Welcome to the last chapter of statics. I hope you've enjoyed your journey up to this point. This last chapter that we will cover is the moments of inertia. Specifically in this video we'll be talking about area moments of inertia, and we'll look at determination using integration first. So to get an idea of what area moments of inertia are, we can look at an example from statistics. Let's say I gave an exam, and for this first exam, exam 1, we have a situation where the average, this is our x bar, is equal to 70%. And let's say you get an 85%, and that's great, you're above average. But how do you compare to the rest of the class, right? There may be this bell-shaped curve, and if you saw that, you kind of know where you fit, right? In exam 2, a similar situation, same average, and same score you got. But if you look in this case, there's very few people that have got above you on as far as an 85%. On this first exam, there's more students that got above you. Well, the way we measure this is by looking at what we call the standard deviation. Right? Standard deviation is a measure of how the distribution is spread out from and away from the average or the mean. This spread means that if it's a small value, that the spread is very close to the mean. If it's a large standard deviation, then it is spread out a lot further. So moments of inertia essentially are like this standard deviation kind of thing. So how does this work as far as what we want to know, right, as far as area moments of inertia? If I have these two beams that I construct out of the same size of 2x4, so I have 3 2x4s, I can make two different beams, beam A and beam B, and it's contained or put into this wall at this location. It's mounted there, and I apply a load P on both of these. Which of these do you think would bend more? Would beam A bend more, or would beam B bend more? Well, if you actually did this experiment, you would find that beam A would bend more than beam B. And why is that? And the reason for that is because we have something called the area moment of inertia, where we have this area away from this x-axis here. On either one of these, we see that we have more area away from it, right? Farther away from it. And that gives us a larger moment of inertia, which gives us more stiffness in our beam. So we can make a stiffer beam with the same amount of material as the smaller beam, as opposed to making it a solid beam. Okay, so how do we calculate area moments of inertia? The area moment of inertia is defined to be this Ix. This is the moment of inertia about the x-axis, and it's the integral of the area times the y tilde squared dA. And y tilde is this value here, of course, which is the distance to this x-axis, right? And x tilde is the distance to the y-axis. So this is our y moment of inertia about the y-axis. So how does it want to bend around the y-axis? How does it want to act when it bends around the x-axis? How much area is away from those two types of axes? And then we also have what we call the polar moment of inertia. We can look at this r tilde and calculate that. Okay, and r tilde is equal to x squared plus y squared, right? That's just our, by geometry, we know this. Okay, so these x tilde, y tilde, and even the r tilde are like moment arms, right? Hence, moments of inertia are often called second moments of an area. And since the moment arms are squared, that's why we get the second moments, is what it's called. So the area moments of inertia are properties of the geometry of an area. So this is really key, is that they are properties of the geometry of an area and are located and oriented about the x and y axes. That's the important key or thought about this. Area moments of inertia have units of length squared, so we will typically see inches squared or millimeters, not squared, to the fourth power, and millimeters to the fourth power, or meters to the fourth power. Those are very typical type units we will see. The area moment of inertia are always smallest about the centroidal axis of the area. So if we can find the centroid of a shape, it will have the smallest area moment of inertia about that axis. And lastly, just a final comment is that this area moment of inertia is very similar to our variance or our standard deviation squared, like we showed in that first example. Right? That variance or standard deviations are measures of dispersion of those exams away from the mean or average, or what we could consider the centroidal axis for the exam kind of a thing. So why are we learning about these and what are they used for? These area moments of inertia are used explicitly in two further on classes that you will take, one being mechanics of material and the other one being dynamics. Area moments of inertia are specifically used in our mechanics of materials class in finding bending and buckling and torsion. All of those are related to this area moment of inertia you will see in there in these equations. Here's the polar moment of inertia. And these are all really area properties that give us properties about the bending, buckling, and torsion. You will also learn about this using mass moments of inertia in the very last section of this chapter, where we will look at angular acceleration and problems like that. That's where it comes in dynamics. So real quickly, if we think about it in dynamics, we may have two batons, and if we put both of these batons, A and B, on a scale, they would weigh exactly the same. But to actually start spinning them, if I wanted to try and get them to spin, which one would spin more easily, right? Which one would be harder to get going or starting to get going? Well, this is the one that's harder to get going. This one's harder to start. This one's easier. Right? And the reason for that is we have this concentrated weight on the very ends of these batons, right? This one is very uniform, and it will be easier to start to spin. One of these properties we want to look at also for moments of inertia is something called the radii of gyration of an area, and it just has a basic definition. It is this k sub x, and is equal to the square root of our area moment of inertia divided by the area. And it will have units of length. So if we go back to our baton example, I could recreate a new baton such as B, where both of these batons again have the exact same weight or same mass. But when I spin them such that they have the same feel. It's just as easy to spin A as it is to spin B. And that may mean in this case that this baton has a shorter shaft in it. It's not the same size as the other one. This K, or radius of gyration of both of these objects, will have the exact same value. So how do we evaluate moments of inertia? In statics, we will evaluate all moments of inertia using integrals, using single integration. And that's at least in this section. I'm not going to have you really do much with the integration in solving area moments of inertia. When we do this, though, we start slicing our objects again. We look at this first one. We have this overall length. We need to find this length or width, W, and dy, and we can find the distance y tilde to the x-axis. It's just from the centroid of that shape. Same with this one here. We have this y tilde to the centroid of the axis. But that one in this case is h over 2. The other one is just simply y. We can calculate this distance of the width based on the equation of that curve, right? So the problem is with the second one, we have this problem with this h squared over 2 and evaluating it, and it really doesn't work well for us. So we have to be very careful when integrating which direction we want to be able to integrate this. So for the work that we would do in this class, when evaluating the moment of inertia about the x-axis, I sub x, we must use an area element parallel to the axis x. When evaluating the moment of inertia about the y-axis, we must use an element that is parallel to the y-axis. So currently that isn't always, we aren't always able to do that because we're squaring these arms, right? But we'll find out in the very next section that we can eliminate this by using something called the parallel axis theorem, and it will make life a lot easier for us. So this example is done in the book for you. I am not going to spend the time doing the integration of this problem for you, but you will find out that it comes out to have these values for the moment of inertia about the centroidal axis, this x prime axis, to be the base times the height cubed divided by 12th, or 1/12 base times height cubed. And around the y-axis, we have a similar type of equation where we have 1/12 the height times the base cubed. Okay. For this example, we were supposed to look at the cross-section of a solid circular shaft and a hollow circular shaft, which are shown below. And we're supposed to compute and compare the polar moments of inertia about point C. One thing I forgot to mention is that if we look back at these equations here, if you look at the back of the book, what's really handy is these simple shapes again, or common shapes that can be used. And if you look, we've used these before for our area and our finding our centroids when we use composite shapes. But we also have very similar equations here that you will see for these shapes for moments of inertia. So on this problem that we're looking at now, we're looking at the polar moment of inertia of a solid shape. So we have this one here, which is pi over 2 r to the 4th. So in this example for A, we have JC, the polar moment of inertia about the centroid is equal to pi over 2 r to the 4th, which is 20 millimeters to the 4th. And that equals, oops, sorry about that. That equals, okay, so it equals 251,327 millimeters to the 4th power. Now what do we have for the second example over here on the right? We have the same equation, JC is equal to pi over 2r to the 4th, and that is our outer, so our large diameter, minus the moment of inertia of the inner one, so pi over 2r inner to the 4th. We can rewrite this equation as just pi over 2r outer to the 4th minus r inner to the 4th. Right? And JC, then if we plug in our numbers, it's just a matter of plug and chug. In this case, we have 20 to the 4th minus 15 to the 4th. And our polar moment of inertia for this example will equal 171,805 millimeters to the 4th power. Okay, well, so what does this mean for us, just to kind of give us some idea looking forward for life? There's something called shear stress, which is equal to TR over J. T is our torque that we would see as a twisting action, R is the radius from it, and J is our polar moment of inertia, and tau is our shear stress. And this is something you would evaluate in a mechanics and materials type problem. But what I point out here is that while we have a smaller moment of inertia for the second one, means that there will be more shear in it for this type of problem, but the amount that we lose because of the center portion of this hollow tube, we don't lose percentage-wise a lot on our shear stress, and we save a lot on material and weight. So using hollow tubes is a very efficient way of transferring torque in a system with a lighter system and a stronger, and not necessarily as strong of a system, but much lighter and a lot less costly. Okay, so that ends the lecture for this first section. And while it is on integration, you will find that we won't be doing that so much in this class right now. I want to spend more time concentrating on using composite shapes and the parallel axis theorem. You will find that very useful going forward in the next classes.